Hello everyone. In this presentation, I'll cover a simple, general, and efficient technique for taking linearizable snapshots of concurrent data structures. Concurrent data structures have received a lot of interest in recent decades because they are important for many applications. Lots of practical concurrent data structures have been developed for stacks, queues, trees, and so on. But most of the existing work focuses on what we call single-point operations, such as insert, delete, and lookup. In many applications such as database systems, it's also important to support what we call multi-point queries. These are queries that need to access large parts of the data structure at the same time. Examples include range queries, snapshotting, and multi-lookup. These kinds of queries are often difficult to implement in the presence of concurrent updates. Most of the work in this area has focused on supporting the range query operation in particular, and the techniques they propose often only apply to a limited set of data structures. Our paper presents a very general technique for implementing multi-point queries. Starting from an existing concurrent data structure, we saw how to efficiently take snapshots of its low-level state, and from there we saw how to compute multi-point queries on these snapshots. This technique works on almost all lock-free data structures that we are aware of, and some examples include Harris's linked list, Michael and Scott's queue, and several lock-free binary search trees. As a concrete example, I'll focus on the EFRB-BST by Ellen, Fatero, Rupert, and Bruegel. Originally, it only supports insert, delete, and lookup, and our transformation adds an additional snapshot operation to it. Supporting the snapshot operation requires making some changes to the original three operations, but these changes add very little time overhead, both in theory and in practice. On the theoretical side, the transformation maintains all the time bounds and progress properties of the original operations. So if they were lock-free originally, then they'll also be lock-free in the snapshotable data structure. The snapshot operation takes constant time, and in fact, it is as cheap as performing a single compare and swap. It doesn't make a copy of the entire data structure. Instead, it returns a handle which can be later used to access parts of the snapshot. You only have to pay for the parts of the snapshot that you access, and you can dynamically choose which parts to access. Using the snapshot operation, we can efficiently support arbitrary multi-point queries by adapting standard sequential algorithms to run on the snapshot. And some examples are listed here. These multi-point queries are weight-free and linearizable, and they also perform well in practice. The properties listed here are not specific to binary search trees, and similar results can be shown for other data structures as well. As an added bonus, our technique is very easy to apply, and we only require single-word compare and swap. The chart below shows how our approach compares with existing lock-free solutions. The y-axis represents practical efficiency, and the x-axis represents the number of data structures the technique applies to. On one extreme, we have specially designed data structures for supporting range queries, such as LFCA and Kiwi. And on the other extreme, we have software transactional memory, which is able to make any sequential data structure concurrent. But they are often not as efficient as hand-designed data structures. Our technique is not as general as software transactional memory, but we found that it overall outperforms state-of-the-art specially designed data structures. There has also been some work on other general techniques for range queries and iterators, but these are slower and more restrictive compared to our approach. Okay, so let's take a closer look at how this approach works. We'll continue our example of adding multi-point queries to a lock-free BST. In this data structure, the left and right pointers of each node are stored in compare and swap objects, and applying our technique just involves swapping these CAS objects for version CAS objects. These are new objects that we define. Essentially, a version CAS object is a CAS object that keeps a history of all its previous values. It supports vRead and vCAS, which behave just like regular read and CAS, along with two new operations, take snapshot and read version. Take snapshot atomically captures the state of all version CAS objects, and read version is used to read from the snapshot. In the next slide, we'll define how these two operations work in a small example with just two version CAS objects, and we'll later see how that applies within a lock-free BST. Consider the following execution. First, the take snapshot operation executes and creates a snapshot S1. After it is linearized, Any changes to x and y will not affect the snapshot. So for example, there could be a compare and swap changing x to 3 and y to 5. Multiple snapshots can exist at the same time, so we can take another snapshot called S2. The read version operation lets us read from both snapshots. It takes as input a VCAS object and a snapshot handle, and it returns the appropriate value from that snapshot. In terms of time complexity, we are able to implement vread and vcast in constant time, which is one of the challenges in this paper. Our take snapshot operation also takes constant time, and it does not actually make a physical copy of all the objects. Making a copy would be expensive for multi-point queries that only access a small part of the snapshot. Instead, some of the work is shifted over to the read version operation. Our implementation guarantees that read version is weight-free, and we'll discuss its exact time complexity after presenting the algorithm. We'll begin by describing a basic implementation that achieves all these theoretical bounds, and then we'll talk about how to optimize it in practice. Let's zoom into one VCAS object in our previous tree example. Each version CAS object is represented internally using a version list, sorted from newest to oldest. Whenever a new version gets added, it is assigned an up-to-date timestamp. Version lists have been around for a long time, and they've been frequently used to implement multi-version concurrency control in database systems, as well as software transactional memory systems. These version lists are usually implemented with locks. Lock-free solutions do exist, but they are often expensive. What makes this difficult is the need to atomically create a new node in the list, and at the same time give it an up-to-date timestamp. Our VCAS operation solves this problem by first linking in a new version with timestamp TBD, and then updating this to the current timestamp. If any process sees a node with timestamp TBD, it has to help update this timestamp to the current time. This update is done using a compare and swap so that only one process succeeds in the update. So a vread operation works by first helping to update the timestamp of the most recent version, and then returning the value stored in that version. The take snapshot operation simply increments the global timestamp and returns its previous value. In this example, it would return 5. After this take snapshot operation is linearized, all new versions are guaranteed to have timestamp greater than 5. A read version operation with timestamp t looks for the most recent node in the version list with timestamp at least t. So in this example, if t equals 3, then it would return the value b. And finally, whenever vread, vcast, or read version comes across a node with timestamp TBD, it has to help update the timestamp of this node. In this implementation, read version takes time proportional to the length of the version list that is traversed, and intuitively, this represents the amount of contention on the object since the snapshot was taken. So these are the high-level ideas behind our algorithm, and a full proof of correctness for it can be found in the full version of our paper. So now let's come back to our snapshotable BST and expand out all the version CAS objects that it contains. In the right-hand diagram, the numbers in each version list node represent its timestamp. Notice that this transformation adds an extra level of indirection to the original data structure, which does not affect our theoretical bounds, but it adds a lot of overhead in practice. Later on in the presentation, I'll talk about how to avoid this level of indirection for most data structures. So version CAS objects provide a nice abstraction for implementing multi-point queries. On the EFRB-BST, supporting linearizable multi-point queries is as simple as taking a snapshot and then running a standard sequential algorithm on the snapshot. The time complexity of the multi-point query would be proportional to the sequential time for running the query, plus the amount of contention experienced by the query. Recall that snapshots are accessed using read version, which possibly involves traversing version lists. The contention term measures the number of version list nodes traversed during the calls to read version. This number is upper bounded by the number of inserts and deletes that are concurrent with the query. The EFRB-BST is actually a particularly easy example when it comes to computing multi-point queries. This is because the left and right pointers of the data structure define the contents of the tree at all times. In general, it is not always possible to support multi-point queries in this manner. In the full version of our paper, we formally specify the conditions a data structure needs to satisfy in order for it to supposed to work. Intuitively, we disallow update operations from linearizing back in time. Most data structures that we looked at satisfy this condition, including Harris's linked list, Michael and Scott's queue, and many more. Going back to the results slide, we've now seen how to make concurrent data structures snapshotable using version CAS objects. We also looked at how to compute multi-point queries from snapshots in a wait-free manner. Since version CAS objects support vread and vcas in constant time, this means that we preserve the time bounds of the original data structure operations, along with any parallelism that it comes with. And finally, we've shown that take snapshot can be implemented in constant time with just a single compare and swap. In the next part of this talk, I'll look at how to optimize our technique to make it significantly faster in practice. We present several practical optimizations in our paper, but perhaps the most important one is how to avoid a level of indirection when using version CAS objects. This level of indirection doubles the height of the data structure, so it has a huge impact on performance. Another thing we noticed in our experiments is that workloads with extremely frequent multi-point queries end up being bottlenecked by compare and swaps on the global timestamp. To reduce contention on this timestamp, we implemented an exponential backoff scheme, which we use when incrementing it, and this helped a lot in some workloads. Finally, to avoid keeping old versions forever, we implemented a simple garbage collection technique based on epoch-based memory management. The experiments we ran include all the above optimizations, and in this talk, I'll focus mostly on the first one, but you can find details about all the others in our paper. This is the diagram from earlier, which showcases the level of indirection added by version CAS objects. Once again, the timestamps and version list pointers are highlighted in green. The high-level idea behind the optimization is to merge each version list node with the data structure node that it points to, and the resulting diagram would look something like this. Applying this high-level idea is not quite so simple because each data structure node can be part of multiple version lists, and this means that we might need to merge a single data structure node with multiple version list nodes. In our paper, we show how to handle these situations, and this sometimes requires slight modifications to the original data structure. Our experimental evaluation has two main goals. The first is to understand how much overhead our approach adds to the original data structure, and the second is to compare the performance of our approach with state-of-the-art data structures supporting range queries. We ran our experiment on a 72-core Intel machine with two-way hyperthreading, and we ran experiments both in Java and C++. We'll start by going over the C++ experiments. Our C++ experiments include two lock-free data structures introduced by Arbol, Raviv, and Brown. One of these data structures supports atomic range queries, and the other one only supports non-linearizable range queries. A non-linearizable range query is easier to implement, and it is useful as a baseline to measure the overhead of linearizability. We used our version CAS objects to make the non-linearizable range query linearizable, and the resulting data structure is represented by the blue line. Comparing the orange and blue lines in graphs A and B, we can see that our technique adds very little overhead to the original data structure, so the overhead of linearizability is not that high. Graph C shows that our memory overhead is low as well, despite the fact that we keep around version lists. This is because both data structures use epoch-based collection, so we collect approximately the same number of nodes. Also, our approach for making range queries linearizable is faster and uses less memory when compared to the technique proposed in Arbol, Raviv, and Brown's paper, and this result is shown in the green line. In our Java experiments, we compare with the following data structures, all of which support linearizable range queries. For our implementation, we applied version CAS objects to the EFRB-BST as well as the chromatic tree, which is a lock-free balanced binary search tree. We call the resulting implementations VCAS-BST and VCAS-CT respectively. In this experiment, the red line VCAS-CT has the highest throughput among all the balanced data structures that we ran. VCAS-CT also outperforms all the unbalanced data structures, except for LFCA in the case where range query size is small. The range query size determines how often range queries get invoked, because in this workload, we have 36 threads dedicated to constantly performing range queries. With small range query size, range queries get invoked much more frequently. This means that in our approach, the global timestamp gets incremented more frequently as well, and it eventually bottlenecks performance. This same bottleneck is experienced by EFRB-BST and Kiwi, but not by LFCA. Rather than using a global timestamp, LFCA synchronizes range queries and updates by having update operations help ongoing range queries. This causes problems in the opposite case where range query size is large, because update operations have to spend a lot of time helping the large range queries. So there's a trade-off between our VCAS CT and LFCA depending on the range query size. When compared to the data structures other than LFCA, our approach has higher throughput in both the update and range query graphs. For this experiment, we generated keys from a uniform random distribution, and this means that the unbalanced trees are still balanced in expectation. We also ran a workload with nearly sorted keys, and this showed a big separation between all the balanced and unbalanced data structures. These are just some of the experiments that we ran, and our paper covers a variety of other workloads as well. Overall, we found that our approach adds very little overhead to the original data structure, less than 9% on most workloads. Furthermore, our general purpose approach is often as fast as or faster than state-of-the-art lock-free data structures that were specifically designed to support range queries. So in summary, we show how to use version CAS objects to make concurrent data structures snapshotable. These snapshots can then be used to support arbitrary multi-point queries. The benefit of our approach is that it is easy to apply and efficient both theoretically and practically. It is also general in the sense that it applies to a large class of data structures and supports a wide range of multi-point queries. So that's the end of this presentation. Thank you for listening, and if you're interested, our code is publicly available on GitHub.